Welcome to Unit 3 of this course. In the first unit, we saw how to model controllers as transition systems. The second unit was an introduction to the model checker, USMV. We also did some examples and exercises. In this unit, we will look at more properties that can be checked on models. Let us start this module with a problem in concurrency. Let P0, P1, P2 and P3 be processes. S0, S1, S2, S3 be some shared resources. S0 is shared between P0 and P1. S1 is shared between P2 and P1. S2 is shared between P3 and P2, and finally S3 is shared between P0 and P3. A process can execute only if it has access to resources on both sides. For example, P1 can execute only if it has access to resources S0 and S1. Here, if I is 1, you would get that it has access to resources S0 and S1. Similarly, P2 can execute only if it has access to S1 and S2. P3 can execute only if it has access to S2 and S3. For P0, it can execute only if it has access to S0 and S3. For P0, Si is S0, but Si minus 1 is P minus 1. However, we have to count modulo 4. In the sense, minus 1 is 3 modulo 4. This is just a way to say that P0 can execute only if it has access to S0 and S3. The problem now is that there is an operating system which schedules these processes based on the availability of resources. The question is, how should the processes be scheduled so that every process gets to execute infinitely often? This is a canonical problem in operating systems. A different version of this problem is popularly known as the dining philosopher's problem. It was proposed by Dijkstra. Here, P0, P1, P2 and P3 are philosophers. S0, S1, S2, S3 are chopsticks. Assume that these are plates. Each philosopher's work is to think and to eat. To think and to eat, and so on. To eat, he needs to have these two chopsticks. He cannot eat with one or none, and he is not allowed to eat with hands. So for philosopher P1, he can eat only if he has access to chopsticks S0 and S1. Similarly, P0 can eat only if he has access to S0 and S3 and so on. Just that instead of processes, we call them philosophers. Instead of shared resources, we have shared chopsticks. The question is, what should the protocol be so that every philosopher can eat infinitely often? By protocol, what is the rule that these philosophers should follow in order to access the resources so that each one gets to eat infinitely often? This is a very famous problem. Let us now give a protocol for the dining philosophers. This is along the same lines as the mutual exclusion problem. We will try to solve this problem using our model of transition systems. Let us try to give a transition system for philosopher I. Initially, the philosopher I is thinking. then he has two choices. Either he requests for the left stick or he requests for the right stick. Suppose he requests for the left stick. If the left stick is free, now for philosopher P1, his left is S1. Assume that he is sitting facing the plate. His left would be S1, his right would be S0. So for philosopher Pi, his left is Si, his right is Si minus 1. So if his left stick is free, then he can take the transition to the state have left. In the process, he sets that the stick I is with him. Okay, so assuming that sticks is an array, sticks of I is being set to I. Suppose he has left. Now he has to wait for the right stick. If the right stick is free, he can take this transition, and in the process he denotes that the I minus 1th stick is with him, and then he can go to the state where he can eat. This path is symmetric. Here he first requests for the right, then he gets his right, then he requests for his left. Once he has both of them, he can eat. He can keep eating as long as he wants, and then when he is done, he goes to the return state. From the return state, he can go back to think. In the process, he can release both the sticks. He can say that my resources are free now. My chopsticks are free for you to use. This is the model of the philosopher. Let us now try to see a new USMV demo of this model. Let us now write the philosopher module in new USMV. So we define a module philosopher which takes as input three parameters: its number, the left stick, and the right stick. What are its variables? We need to define its locations. The locations are think, request right, request left, have right, have left, eat, return. Yes, that's it. What are the transitions? The initial value of location is think. Let us now define the transitions. Next of location is as follows. If location is think, he can either keep thinking, or he can request for the left stick, or he can request for the right stick. If location is request left and the left stick is free, assume that this gives us the fact that the left stick is free. We will then call it appropriately in the main module. So if location is request left and the left stick is free, the philosopher goes to have left. Now, if the location is have left and if the right is free, then he can go to eat. Similarly, if location is request right and the right is free, he goes to the state have right, and if location is have right and the left is free, he goes to the eat state. When he is in the eat state, he can continue eating or he can go to the return state. And once he is in the return state, he goes back to the think state. Now we need to define the next for the variables left and right. Next of left, if you see, this is the left stick. If the location is request left, then the left stick should be set to the value I. And when going back to think, the left stick should be made free again. Let us now write it. If location is request left and the left is free, my location goes to have left and my left should be set to I. Now if location is return, the left should be set to free. This will become clear when we write the main module. Now what about next of right? If location is request right and the right is free, then right should become I. At the same time, if location is return, then the right should become free. We still have missed something. In this path, if you are in have right and the left is free, then you go to eat. So in this transition again, the left should be set to I. Similarly, here the right should be set to I. Let's come back here. If location is have right and left is free, then set your left to I. Similarly, if location is have left and left is free, right is free, then set the right to be I. We are more or less done. However, we need to give the statement which says that if none of the conditions match, stay in the same location. Finally, to location. We have written the philosopher module. Now let us write the main module. Module main. What are the variables? We will now define a variable denoting sticks. It is going to be an array of size, the number of philosophers. Let us say the number of philosophers is 4 as given in the slides. So 0 to 3. Each cell of the array is made of values from this set. Either it can be free or it can be 0, 1, 2, 3, denoting the fact that philosopher 0 has access to that stick. Essentially, sticks of 0, sticks of 1, sticks of 2, sticks of 3, each of them contain either free 0, 1, 2 or 3. Let's now define the philosophers. Philosopher 0 is a process philosopher. His number is 0. If you remember, we have 3 inputs to philosopher. His left stick is sticks of 0 and his right stick is sticks of 3. Similarly, philosopher 1 is process philosopher. His number is 1, his left is 1, his right is 0. Let me complete. Philosopher 2, his number is 2, his left is 2 and his right is 1. Finally, philosopher 3, process, philosopher 3, his left is 3 and his right is 2. We will now run this code in USMV. Let us now run this code. I have saved it under Philosopher demo. Let me call it using USMV demo.smv and now go. There seems to be a syntax error. Let us check. It says at line 29 there is a syntax error. Line 29, yes, I had forgotten the semicolon here. I'll save it. Now let me run it again. New SMV Philosopher demo. There seems to be another problem. Cannot assign value have right to variable sticks of 3. Line 18. So the error is here. This should be left and here it should be right. So this was the error. Let's run it again. New SMV Philosopher demo. Yes, it has successfully executed. Let us now try to simulate the model. What is the initial state? If you see, there seems to be some error. It says too many future states. This is because we have not specified the initial states in the main module. So in the main module, we should have given the initial values for assign initial value of sticks of 0 is free, initial value of sticks of 1 is free as well, initial value of sticks of 2 is free, and finally init of sticks of 3 is free as well. Let's hope that we can run it successfully this time. New SMV Philosopher. Let's now try to pick an initial state to see if it works. Yes, it does. There is only one initial state, and in this initial state, all the philosophers are thinking and all the sticks are free. Let us now try to simulate this model to understand certain things. Simulate -I -k, say for 15 steps. We started with all of them in the think state and all sticks free. There are multiple available successors. Let us take this successor which moves to the philosopher 3 going to the request left state. From thinking, philosopher 3 moves to request left. This is state 0. From state 0, these are the possible successors. Let us choose one successor. Let us choose this successor where philosopher 2 is also moving to the request left state. This is successor 0. Now, let us choose the successor where philosopher 1 moves to request left. And finally, let us now choose the successor where philosopher 0 moves to request left. Right now, all sticks are free and all the philosophers have moved to the request left state. Now, what could the successors be? This says that if process main is selected, then there is no change. This is the state where philosopher 3 now moves to the have left because sticks of 3 is free. Philosopher 3 can have his left stick and then he sets sticks of 3 to be 3. Let us choose state 1. From state 1, there are multiple successors. In this successor, okay, let me explain. This is the one where nothing has changed. This is the result of process main being selected. So none of the philosophers is executing his step. State 1 is when philosopher 3 goes to the eat state. State 2 is when philosopher 2 moves to have left. So right now philosopher 3 is already in have left. Philosopher 2 also moves to have left and he sets sticks of 2 to 2. This is state 2. Now from here, let us choose the state where philosopher 1 moves to have left. So philosopher 3 is already in have left, philosopher 2 is in have left, and philosopher 1 moves to have left as well. This was state 2. And now I will once again choose the situation where philosopher 0 takes his left stick, sets it to 0, sticks of 0 to 0, and then moves to have left. This is state 4. So currently, all the philosophers have taken their left stick. What could the possible successors be? There is only one successor, which is the same state. It just says that this is reachable through different selection of processes, but no matter whatever process you select, you get back to the same state. Let me choose, say the process selector is philosopher 2. Nothing happens. If you see, all of them have moved to a scenario where they have the left stick alone. Since none of them can go to the eat state, they cannot release the stick. So this is a situation where all of them keep waiting for the right stick. No matter whichever philosopher is chosen to proceed, the state remains the same. If you see, it always stays in the left, have left scenario. This kind of a scenario is called a deadlock. From the initial state where all the philosophers were in the think state, the system has reached a state where each of the philosopher processes is in the have left state. And the sticks is like this. Sticks of 0 contains 0, sticks of 1 contains 1, sticks of 2 contains 2, and sticks of 3 contains 3. This process cannot move ahead because sticks of 1 is not free. Similarly, none of the processes can move ahead because the sticks are not free. Since none of the processes can move forward, this situation is called a deadlock. The question is, how do we detect such deadlocks in models? What we did now was a simulation. I forced certain transitions and I showed that there is a deadlock scenario. But suppose you have a model in your hand and you want to check if such kind of deadlocks are present in the model, what should you do? This is going to be the subject of this unit. What properties should be checked to detect deadlocks? We will try to answer this question in a step-by-step manner. I hope that the question is clear. We saw this model of the dining philosophers. It's a concurrent system. The model had a deadlock. Now the question is, how do we detect such deadlocks using USMV? Are there certain properties that we can check instead of doing this manual simulation? Are there some properties that we can check so that the deadlocks are revealed? Now in the step-by-step procedure, in module 2, we will first attach a mathematical meaning to the word properties. In module 3 and 4, we will see different examples of properties. They will still not be able to detect deadlocks. Finally, in module 5, we will explain certain properties and ways of checking these properties in USMV, which will reveal deadlocks.